recording, hopefully. Okay, right. So we just derived before the break. We have stress deflection equal to Py over AE, and then I show you the operating boundary of the equation. Okay. Next, I'm going to write out the notation before we go into the example. So the notation for elastic deformation. You all can hear me, right?
Yes, we can.
Thank you. Notation for elastic deformation. So elastic deformation has two modes. Under axial loading, okay. I better be specific. Oh, oops. What happened? Oh, something happened to my, yeah, it's probably it crashed. So elastic deformation under tensile loading or under axial loading has two modes. And they are known as tensile or compression. So if we have a member, right, and the load are pushing outwards, the coupled load is pushing outwards about its neutral axis, then the deflection, stress, and strain, they're all going to be positive. Okay. And if the structure, so this is tensile, and if the load are acting towards the member, this is what we call compression. And in compression, the deflection, the stress, the strain, they are all in negative. Okay. Now this is for elastic deformation. Okay, elastic deformation. When we do static analysis, right? Let me recall back when I wrote up static analysis. When we were doing static analysis, okay, our positive and negative is depending on our transformation, yes or no? So for this case, where summation forces of y, x, and rotation about z is positive, is because we apply the right hand rule, right? So this is our x and y, and if your thumb will be pointing outwards, and when you close your fingers, right, your thumb will be pointing towards you, right? X must touch y. This is your rotation about z. Okay, so static analysis is dependent on your transformation. For elastic deformation, tensile is positive, compression is negative. Okay, so from here we are going to go into our example number 1. So example number 1 can be acquired from Avenue to Learn. I put lecture 1, right? So you can download the PDF of it. Okay, so let's look at example number 1. Okay, let me copy everything from example number 1 first. Okay. Okay. So you can see for portion of the rod ABC, right, are made of aluminum from which the Young's modulus is 70 gigapascal. Knowing that the magnitude of P, right, is 4 kilonewton, right, determine the Q value so that the deflection at A is equal to 0. Okay, and then we have to find the corresponding deflection of B. Okay, so this is what we have to do. Okay, so just to quickly write this out. So we know that the Young's modulus is equal to 70 gigapascal, right? And we are given that P over here, okay, we are dealing with 4 kilonewton. Okay, so determine the value of Q, okay, such that the deflection at A is equal to 0. Okay, so the deflection, so even after the 4 kilonewton, right, we have to find what is Q such that A, the deflection at point A, okay, is equal to 0. So no change in length. No doubt we have a tensile of 4 kilonewton. Okay, then we are asked to find the deflection of point B. Okay, so we know, okay, so sorry, not we know, okay, so we are aware that we have to apply the formula where deflection is equal to PL over AE. Okay, this is what we know so far, right? Where deflection is PL over AE. Okay, then we are going to, we also know that if the structure is under tensile, right, i.e. deflection, stress, and strain are positive, right? If you apply this rule, right, and then when it's compression, or apply this formula PL over AE, your deflection, stress, and strain, they are all negative. Okay, so you have to obey these rules. Okay, so why obey these rules? Because I'm going to draw our transformation to declare that this is X, Y, and this is rotation about Z. Okay, whether it's positive or negative based on elastic deformation, right, has nothing to do with whether this Y is positive or negative. Has to do whether is it tensile or in what? Compression mode. Are we clear? Okay. So what we see is this. This structure has two different cross-sectional area, right? And it also have loads applied at point B and point A. Okay. So we have to divide this structure. Okay, we have to divide this structure. So I'm gonna look at the rules to divide this structure. Okay, so the first rule where you have to divide the structure is where the load are applied. Right? So this is one of this rule, one of the rule. Okay. The second rule, okay, now where the loads are applied. So we know that the load is applied at point B and point A, right? So when that's the case, I'm going based on the load, I'm going to call this section 1, and this is section 2. Okay. The next thing where the next one, so this is based on load. The next one where there's a change in geometry. Okay, where there's change in geometry, i.e. either in diameter or length. So when this, if we just look at the change in geometry, okay, either in length or diameter, again, we have to divide this structure into what? Into 2. Okay. And the third rule is depending if there's any change. Okay, is there any change in material type? For this case, no, okay, because both are what? AB and BC are all aluminum. If AB, this is just a if, okay, a different question, okay. If this is made of brass and the lower one is made of aluminum, okay, then you have to divide them into 2 also, okay. So you select based on the biggest number of division. So for this case, where the load are applied, you have to divide into 2 sections. The change in geometry is 2. The change in material type, there's only one material type, so you don't need to divide them. So you pick the highest division. So for this case, you divide them into what? 2. Are we clear? Okay. So that are the rules of how to section the structure. Okay. Then we know, right? The next thing we know is that what we want to determine is Q, right? So the total deflection is equal to deflection of AB plus by deflection of BC, right? Is the total deflection. Okay. So now we want to find the deflection of AB and we want to find the deflection for BC. But based on the condition that we are given, okay, based on the condition that we are given, okay, i.e. deflection of A is equal to 0, okay. For this formulation, right, for this problem, our total deflection must be equal to 0. However, the load of 4 kilonewton has to be there, and we have to find what is the load at point, or what is the load Q applied at point B. Okay, so let's gather the information that we have first. Okay, so the formula that we're going to apply is PL over AE, right? So we look at section, right? We look at section AB first. Okay, we look at section AB.
Sorry, sir, why is the deflection 0 again?
Because the question said that the deflection at A is equal to 0. A cannot move.
Oh, okay.
So, i.e. the total deflection must be equal to 0. Okay, but you have load applied. Means when you have load applied, the material will respond, yes or no? That's why P will make A go up, yes or no? It's tensile. B, right, at Q, it will pull it what? Downwards, you'll pull it back. Okay, so that's where we want to find Q now. Okay, so now, so if we look at section A, right, so we know that LAB, length of AB, so let's gather our information first. It's equal to 0.4 meter. Okay, and then we are going to calculate area of AB, which is equal to pi. So what is given to us is diameter, so we change to radius, so it's 0.01 squared. So calculate everything in meters. So 0.01 squared times by shift pi, so it's equal to 314 0.159. Now, whatever we do, we leave to, in terms of geometry, we leave to 3 decimal places. I repeat again, anything in geometry, you